Have you ever thought about how a doctor can figure out what's going on inside your body from just one little sample? I mean, what if I told you the answer is sometimes as simple as watching a blue liquid turn red?
All right, let's get right into it. Today, we are cracking the code on a really fundamental tool you'll find in labs and clinics all over the place, the Benedicts test.
So, here's the game plan for our little investigation. First, we'll tackle the main mystery of what this test even is. Then, we'll go behind the scenes to see the chemistry of that color change. After that, we'll get our hands dirty with the user manual, learn how to decode the results, and finally, open up the case files to see how it's used in the real world and where it falls short.
All right, first things first. What in the world is this test we're talking about?
Okay, think of Benedict's test as a little chemical detective. Its whole job, its one and only mission, is to hunt for something called reducing sugars inside a liquid sample. So that kind of begs the question, right? What exactly is a reducing sugar? Well, just imagine a simple sugar like glucose as this super generous molecule. It's got this special little part of its structure that lets it give away electrons really easily. And that generosity, that ability to donate electrons, is exactly what makes it a reducing sugar. That's the secret sauce for this whole test.
Okay, so how does this whole electron-giving thing create that awesome color change we talked about? This, my friends, is where the chemistry gets really cool.
So the Benedicts reagent itself is like a little chemical team, and each player has a super specific job. You've got copper sulfate. That's the one that brings the blue copper ions to the party. Then there's sodium carbonate, which sets the mood, creating just the right alkaline conditions. And finally, you have sodium citrate, which is kind of like the chaperone, keeping those copper ions from getting out of hand before the reducing sugar shows up.
Now, when you add some heat to the mix, things get interesting. If there are any of those reducing sugars in your sample, they start doing their thing, donating those electrons to the blue copper ions. This little gift of electrons literally transforms the blue copper, or Cu2+, into a whole new thing, red copper, or Cu+.
And these new red copper ions, they don't mess around. They immediately team up to form copper 1 oxide. Now, this stuff is a solid, so it won't dissolve in the water, and its color, you guessed it, a super distinct brick red. That's the big color change we've been waiting for.
All right, so we've got the why figured out. The chemistry makes sense. But how do you actually do the test? You're going to be surprised. It's actually incredibly straightforward.
It's basically a 4-step deal. First, you pop a little bit of your sample into a test tube. Next, you add the blue Benedict's reagent. Step 3, you heat the whole thing up in a boiling water bath for just a few minutes. And then, the final step is the easiest. Just watch. Seriously, just observe what happens. The colors are going to tell you the whole story.
Okay, so the test is done. You're looking at this test tube, and it's definitely a different color now. But what does it all mean? It's time to decode the results.
See, this is what's so cool about this test. It's not just a simple yep or nope. It's what scientists call semi-quantitative. If your tube is still blue, well, there's no reducing sugar. You're all clear. But if you see it turn green, or yellow, orange, or that deep brick red, that not only confirms that reducing sugars are there, but it also gives you a rough estimate of how much. It's like a color-coded scale. The warmer the color gets, the more sugar there is.
Now you might be thinking, hey, isn't there another test called Felling's test that does the same thing? And you'd be right. They're very similar, but Benedict's is usually the go-to. Why? Well, it's just more stable. Remember that sodium citrate stabilizer we talked about? And it's also a bit more sensitive, so it tends to be the more reliable tool in the toolbox. All right, we've solved the chemical mystery, we've cracked the color code. Now let's open up the case files. Where is this test actually used out in the real world? And just as importantly, what are its limitations?
You know, for such a simple test, it has some seriously powerful applications. In a clinical setting, it's a super fast way to check for glucose in urine, which can be an early red flag for diabetes. In biochem labs, scientists use it to figure out what kind of unknown sugars they're dealing with. And even the food industry uses it for quality control, checking for simple sugars in products. But, like any detective's tool, it's not foolproof. You gotta know its weaknesses. For one, certain drugs can actually trigger a false positive, messing with your results. Other things, like vitamin C, can interfere with the reaction too. And probably the biggest thing to remember is that it's not specific. It'll detect any reducing sugar, not just glucose. That's a really key point. And it's why this test is seen as a great starting point, a preliminary test, but not the final word.
You know, this quote really nails it. For all its limitations, the biggest strength of the Benedict's test is just how simple and efficient it is. It gives you a yes or no answer, that's the qualitative part, and a how much estimate, that's the semi-quantitative part. And it does it all super quickly with very few materials.
So, at the end of the day, we've seen how a simple color change, just a shift from blue to red, can tell us so much about the hidden world inside our own bodies. And it kind of makes you wonder, right? If this one simple reaction can be so revealing, what other incredible secrets are just hiding out in basic chemistry, waiting for us to find them?